Hello and welcome everyone. My name is Mona Yadav and in this video we will start learning about properties of fluids. So as we have seen in the previous video that there are various properties such as density, specific weight, specific gravity, viscosity, pressure, temperature, specific heat capacity, etc. So and we are going to learn these properties based on their definition, calculation, units, interpretation, application and considerations. So let's move ahead with the density. So what is density? Density is a fundamental physical property that quantifies how much mass is contained in a given volume of a substance. How much mass will be there occupied in a particular volume of a substance. It is typically denoted by the symbol rho and it is expressed in units such as kilograms per cubic meter, which can also be said as kg per meter cube in the international system of units, SI units, or grams per cubic centimeter, gram per centimeter cube in the CGS system. The density of a substance is calculated using the formula. Now, the formula is based on definition. And what is definition? Density is a fundamental physical property. It is a basic property that quantifies what it is going to quantify. That how much mass is contained, how much mass is there in a given volume of a substance. So for a particular volume of substance, how much mass will be contained in that particular volume, that is density. So the formula will be rho equals to m by v, where what is rho? We know that rho is the density of the substance, m is the mass of the substance, and v is the volume of substance. So density can be calculated by the formula rho is equals to m by v, mass contained in a given volume of a substance. Now let's try to understand the density with these diagrams. So in this diagram we can see that there are various states of matter such as gaseous, liquid and solid. Gas, liquid and solid, and the density variation is shown. So we can see for a particular gas that gas is having fewer molecules, and those molecules or the gas particles are separated apart. They are far from each other, they are separated or scattered in a given volume of substance. The distance between two molecules of gases is large, and if the system would have been larger, it would have been having more volume, then the distance between these two particles would have been more. If the system would have been big, then the distance between two particles would have been more. Gas particles are scattered. They are away from each other. Let's study about liquid. So in liquid, we can see that there are liquid particles, but they are separated from each other and they are having a certain distance. The distance is less than the gas particles, but they are not intact to each other. They are not stick to each other. But still there is a small amount of distance between the liquid that if they are allowed to move, they are allowed to move apart from each other, they'll move away. They'll move away. They'll not be intact to each other. They'll not stick to each other. If they are allowed to move, then they can separate away. Let's study about solids. So in solids, we can see that there are a lot of particles. There are large number of solid particles and they are stick to each other. They are bonded to each other. Like they are attached to each other in such a way that they will not separate, which is showing to us that they are densely packed. So that means the density in solid particles is much more than the density of gas particles or liquid particles or liquid. Like in bottom we can see that the gases are having low density, whereas liquids are having moderate density and solids are having very high density. Because gas particles are scattered away, liquid particles are also having some distance between them. They are not closely packed, whereas solid particles are densely or closely packed, bonded or intact towards each other. So this is about density of various states of matter. Now let's try to understand the density through this diagram where we have density of various liquids. Now we can see that the honey is at bottom, and we understand that whatever is heavier, of course it will settle at bottom, and whatever substance is lighter, it will be at the top or it will be at a higher distance as compared to the bottom surface. So from this diagram we can understand that the honey is, as it is settled at bottom, of course it is having more density. Liquid soap is having a density lesser than honey, that's why it is at top of the honey. Water is having a density again lesser than liquid soap, and whereas ethyl alcohol and olive oil are having density less than water, so they are at the top. So from this diagram we can give a conclusion that honey is having highest density, whereas ethyl alcohol is having the lowest density among these fluids. Like some oils have less density than water, that's why they float on the surface of water, whereas honey or any dense liquid, as it is having more density, so it settles down in water, they don't float. So the density of a substance is calculated by the formula rho is equals to m by v. Now we know it. In other words, density represents the amount of mass per unit volume. So if the mass of an object is spread out over a large volume, it will have a lower density, just like in gases, compared to the same mass concentrated in a smaller volume. Now, density is an intensive property. That means it does not depend on the size or amount of the substance being measured. So, whatever the substance we are measuring, irrespective of its amount, the density can be calculated. So, density is influenced by the factors such as temperature and pressure. Okay, this is about density. Let's move ahead on the second property. Next property, that is specific weight, which is denoted by gamma. So specific weight, also known as unit weight, is a measure of weight per unit volume of a substance. Density was mass per unit volume of a substance, and specific weight is weight per unit volume of a substance. It is typically denoted by the symbol gamma and is expressed in the units such as newtons per cubic meter, newton per meter cube, or pounds force per cubic foot. The specific weight of a substance can be calculated using the formula. Now, this formula is again dependent on definition. Gamma is equals to rho into G. So, we can say that specific weight is nothing but density of the substance, but it is also considering the acceleration due to gravity, where this gamma is specific weight, rho is the density of the substance, G is the acceleration due to gravity of the substance. Now, the specific weight of a substance can be calculated using the formula gamma is equals to rho into G. So, in other words, specific weight is equal to what? It is equal to density only, density of the substance, but multiplied by the acceleration due to gravity. So, it represents the force exerted by gravity on a unit volume of substance. The specific weight of a substance is closely related to its density, but it takes into account the effect of gravity. Basically, the specific weight and the density are related to each other, but only through acceleration due to gravity. Specific weight is used in various engineering and scientific applications, particularly in the field of fluid mechanics, hydraulics, and geotechnical engineering. Now, why we need to study about specific weight? Because calculation of specific weight helps us to calculate various forces and pressures and loads in the systems involving fluids or solids. So, let's study about next property, that is specific gravity, denoted by Sg. Specific gravity is a dimensionless quantity that compares the density of a substance to the density of a reference substance. So basically there are two densities. One is the density of the substance for which we have to calculate the specific gravity, and another is the density of a reference substance. So typically water, which is at a specified temperature and pressure. It is often used to describe the relative density of liquids or solids compared to water. The specific gravity of a substance is calculated using the formula Sg of a substance is equals to rho of substance upon rho of water. That is specific gravity of a particular substance to the density of that particular substance divided by density of water. Where again Sg of substance is specific gravity of the substance, rho of substance is the density of the substance, and rho of water is the density of water at the same temperature and pressure. Since specific gravity is a ratio of densities, see, the specific gravity Sg of a substance is what? It is a ratio of two densities. One is the density of substance, another is the density of water. So as it is the ratio of densities, it is a dimensionless quantity and does not have any unit, because both the units will get cancelled because of being same. Now, the specific gravity of water at 4 degrees Celsius is typically used as the reference point, because water has the density of 1 gram per cubic centimeter. So this 1 is taken as the reference. So whose value when converted to SI unit system is 1000 kilograms per cubic meter, kg per meter cube at this temperature. So as a result, substances with a specific gravity greater than 1 are denser than water, while those with the specific gravity less than 1 are less dense than water. So the specific gravity, the density of water or the specific gravity of water is considered as reference. Specific gravity is commonly used in various industries and applications, including like determining the concentration of solution in chemistry and similar industries, assessing the buoyancy of the objects in the fluids, calculating density or volume of materials, quality control in manufacturing processes, designing and analyzing hydraulic systems, etc. So this is all about specific gravity. Let's move ahead with the viscosity. So viscosity is a fundamental property of fluids that measures the resistance of a fluid to deformation or flow. Resistance of a fluid for flowing. Viscosity is fundamental property. It is a basic property of fluid. And what it is measuring? It is measuring the resistance offered by the fluid for flowing. In simpler terms, it is a measure of fluid's thickness or resistance to flow. Viscosity arises due to the internal friction between adjacent layers of fluid. Now, how viscosity arises? There is a friction between internal particles or internal layer of fluids as they move relative to one another or relative to each other. Now, through this diagram, we can understand about the viscosity. So, here we can see that there is a plane surface. It is a plane, and consider that there is a fluid over this plane surface. Now the bottom layer of the fluid will be near to this surface, and as the velocity of this surface is 0, so therefore the velocity of that bottommost layer will also be 0. But as soon as we will move upwards towards the upper layer of the fluids, as see, the example is that there is a plane surface and there is a fluid having certain density, and that fluid is here above plane surface. The bottommost layer will be having very negligible velocity because it is in contact with the bottom surface. But as we will move upwards in the y direction, as the distance from the bottom surface will increase, therefore the velocity will also increase, because they will not be bound to the bottom surface and there will not be any obligation on them for flowing. Like there is no any restriction to them for flowing as compared to the restriction to the bottom layer. So the fluid velocity will go on increasing, and that's why we can say that the velocity profile will be in this way. That velocity will go on increasing as soon as the distance from the bottom surface goes on increasing. So here we can consider that the particle located at this particular point at a certain distance will have u velocity. Whereas if we will move upwards to a point where distance is more, so u will be there, but there will be addition of more velocity, and therefore the term will be shown by u plus du. So that du is the increase in velocity with the increase in distance. So this will be the velocity profile in case of the velocity variation near a solid boundary. So here at this point we have, for this particular fluid particle, we have u velocity. But if we will consider a fluid particle at a more distance, higher distance than this particle, it will have a velocity as u plus du. And it will go on increasing if we will consider a particle higher than this, at a more height than this. So if the distance goes on increasing vertically, then the velocity also goes on increasing. So that conclusion can be taken from this particular diagram. So we can say that the shear stress the shear stress between the fluid particles. The shear stress between the fluid particles will be directly proportional to this velocity gradient. And what this velocity gradient is? Du by dy, change in velocity to the change in distance. Now tau is directly proportional, tau, that is shear stress, is directly proportional to the velocity gradient. So when we will open this directly proportional sign, so tau is equals to mu into du by dy, and this mu is constant of proportionality, also known as dynamic viscosity. So mu is equals to, by simplifying this equation, rewriting this equation, we can have mu is equals to tau divided by du by dy. So this mu is nothing but the dynamic viscosity. So there are two main types of viscosity. One is dynamic viscosity, also known as absolute viscosity. Second is kinematic viscosity. So dynamic viscosity, also known as absolute viscosity, is often denoted by the symbol mu, and it is a measure of the resistance to shear or tangential flow within a fluid. So it is defined as the ratio of the shear stress to the velocity gradient in the fluid, just as we seen in the previous slide. So mu is equals to tau upon du by dy. So dynamic viscosity is expressed in units such as Pascal seconds or Newton's second per meter square in the SI system, or poise in the CGS system. Dynamic viscosity denoted by mu equal to 1 poise. The conversion of poise in Newton second per meter square is 1 by 10. So 1 poise is equals to 1 by 10 Newton second per meter square in SI unit form. So next is kinematic viscosity. So kinematic viscosity denoted by the symbol nu is the dynamic viscosity of a fluid divided by its density. So mu by rho. So it represents the fluid's resistance to flow under the influence of gravity and is a measure of fluid's internal friction. So kinematic viscosity is the measure of fluid's internal friction, friction between internal fluid particles. So it is denoted by nu equals to mu by rho. So kinematic viscosity is expressed in units such as square meters per second, that is meter square per second in the SI unit, or Stokes in the CGS system. Kinematic viscosity denoted by nu equal to 1 Stoke in CGS system, equal to 1 centimeter square per second, which can be converted to 1 by 100 the whole square of meter square per second in SI unit form. Now as 1 meter equals to 100 centimeter, similarly 1 Stoke equals to 100 centistoke. Now the relation between kinematic and dynamic viscosity is what? So the relation between kinematic and dynamic viscosity arises or comes with the help of density. Kinematic viscosity is the dynamic viscosity of a fluid divided by its density, that is rho. So nu is equals to mu by rho. So this is about viscosity. Now let's see viscosity through the diagrams. So for water, the viscosity is lesser because the intermolecular bonds are weak in case of waters, whereas for olive oil, the viscosity is medium. The strength of the molecular bonds is more as compared to the water, whereas in case of honey, so the molecular forces between the bonds are very strong intermolecular bonds. That's why the viscosity in case of honey is higher. So viscosity in case of water is lower. Viscosity in case of olive oil is more than that of water, but viscosity in case of honey is much more than that of water and olive oil. So viscosity is what? It is influenced, it is a property which is influenced by factors such as temperature, pressure, and the molecular structure of the fluid. Generally, fluids with higher viscosity flow more slowly than those with the lower viscosity. So fluids with the higher viscosity, like honey, they will be moving slowly. Whereas fluids with lower viscosity like water, so they will be having very high velocity. For example, honey has a higher viscosity than water, so it flows more slowly. So viscosity is a critical parameter in various applications, including fluid dynamics, engineering, and material science. It affects processes such as fluid flow in pipes, lubrication of machinery, mixing of fluids, and heat transfer. So understanding about viscosity is essential for designing systems and processes involving fluids. So wherever there are fluids, we need to be aware about its properties such as viscosity, density, and so on. So for optimizing their performance. So next is Newton's law of viscosity. Newton's law of viscosity, also known as Newton's law of fluid friction, describes the relationship between shear stress and the velocity gradient in a fluid undergoing laminar flow. So through this diagram, we can understand the relation between the velocity and the distance and how the velocity gradient appears. So that we have seen while learning about viscosity. So as soon as the distance is increased, vertical distance is increased, so the particles have more velocity. The fluid particles have more velocity as they are moving away from the bottom surface. So there is a velocity gradient. So tau is equals to mu into du by dy. Now why this happens? Because the bottom surface, the bottom surface is stationary. So the fluid particles in contact with the bottom surface, they'll also behave as stationary. But the fluid particles above that surface, they'll have a little bit higher velocity, and as soon as we will move upwards, the particles will have more velocity, they will be free to move, and that's why as soon as the upwards distance is increased, the velocity is also increased, and that's why there is velocity gradient. Now Newton's law of viscosity states that the shear stress between adjacent fluid layers is directly proportional to the velocity gradient perpendicular to the direction of flow, and constant of proportionality is the dynamic viscosity of the fluid. So tau is equals to mu into du by dy, where tau is the shear stress, du by dy is velocity gradient, that is change in velocity. Du is what? Change in velocity. Dy is change in distance. Change in velocity per unit distance perpendicular to the direction of flow. Mu is the dynamic viscosity of the fluid. So in simpler terms, in simple language, we can say that Newton's law of viscosity states that the force required to maintain a constant velocity gradient in a fluid is proportional to the viscosity of fluid and the rate of change of velocity with respect to distance. So this is another way of expressing Newton's law of viscosity, that shear stress is what? Shear stress is nothing but force upon area. So force required to maintain a constant velocity in a fluid is proportional to the viscosity of the fluid. This relationship holds true for fluids undergoing laminar flow, where the fluid flows in parallel layers. Laminar flow is what? So in case of laminar flow, the fluid flow will be in form of layers, and one layer will not interfere in between another layer. So in laminar flow, the velocity profile of the fluid is linear. The flow is predictable and the flow is stable also, because one layer will not come in contact with the other layer. We can see it in diagram. So this is the example of laminar flow. One fluid particle will not interfere in the motion of another fluid particle. So the flow will be in form of layers. Whereas this is the turbulent flow, where there may be formation of eddies, or there may be circular motion, or like turbulent flow can occur. So Newton's law of viscosity holds true for the laminar cases of laminar flow. So this is all about Newton's law of viscosity. This is very important for calculating the viscosity or shear stress, like in case of many numericals which are based on Newton's law of viscosity. So understanding of Newton's law of viscosity can be helpful in solving various numericals. So we'll be solving various numericals in coming videos. Thank you.